Let me do a share screen, I think. Can you see my screen? I don't think you do. Is everything okay? Are you all fine, by the way? Is there anybody who want to share something in this forum? Feel free.
Depressing, that's all.
What?
I said it's depressing, the situation, that's all.
I agree. It's a depressing situation. I agree. Since we cannot do much about the situation, what we can do is to try to get ourselves entertained by some good stuff in physics. And hope that everybody will, do good stuff in physics rather than shoot missiles at each other. All right. So last time we still discussed curvature. So quick recap on what we did. So I introduced the concept of curvature. We talked about the curvature tensor. We talked about parallel transports. Then we talked about the curvature tensor. Right. Then we discussed various properties of the curvature tensor. Right. I showed you with giving you semi-proof, not a full proof, of a mathematical theorem that states that the zeroth of the curvature tensor at any space point in any location in space-time, plus a metric that has 1 negative and 3 positive eigenvalues are necessary and sufficient conditions to ensure that the metric is flat. We spoke about a few algebraic properties. Of the curvature tensor, right? We spoke about symmetry, anti-symmetry with respect of a change of the first pair with the second pair, right? R rho sigma mu nu is R mu nu rho sigma. Then we talk about anti-symmetry with exchange of two indices, two nearby indices, right? So R rho sigma mu nu is minus R sigma rho mu nu is minus R rho sigma nu mu is plus R sigma rho nu mu. If you take one of the pair, the first pair, and one of the second pair, and you interchange them, it's anti-symmetric. We spoke about cyclicity, right? In the last three indices, right? So R rho sigma mu nu plus R rho mu nu sigma plus R rho mu sigma mu is equal to 0. We introduced the Ricci tensor. R mu nu is R lambda mu by contracting the first and third indices. And the Ricci scalar R just R mu mu. And we specify that in n dimensions, all these properties means that the number of independent components is 1/12 n squared minus 1 in n-dimensional space. So in the 4-dimensional space, we end up with a 20 independent component of the Riemann. In 2 dimensions, it's only 1. In 1 dimension, there are no independent components, 0. And then finally, we discussed the Bianchi identity. Identity. There's several Italian guys that made substantial contribution to this field, right? Which is again, it's a important differential identity. Right? So if you take the covariant derivative of with respect to lambda of r, a rho sigma mu mu, and then you take the cyclic permutations of that of all the first three indices. So lambda rho r sigma lambda mu mu plus lambda sigma r lambda rho mu mu are equal to 0. And then we also introduced the Einstein tensor. G mu mu is r mu mu minus 1/2 r g mu mu. And the Bianchi identity automatically tells that the covariant derivative of that is equal to 0. Lambda mu g mu mu is equal to 0. And then we gave a few examples. Questions before we proceed?
Yes, I have a question. I understand that if the Riemann tensor is 0, so there is no curvature, so everything's fine. But if he has some, one index and up to all the symmetries, one index that is not non-zero, can we have some physical interpretation like why this is non-zero and the other are 0, or what does this mean in terms of curvature in this? I don't know. We just said, okay, there is some curvature.
Okay. That if it's non-zero, that means that the space is not flat, right? Now, remember that in some sense, the metric was defined arbitrarily, right? I mean, you choose which is the x direction, which is the y direction, right? You could have chosen it like that.
Right.
So in that sense, it's somewhat arbitrary, right? Now, of course, the Riemann tensor depends on is derived from the metric. So so the answer is, if I understand correctly, your question, on the one hand, saying that the Riemann is non-zero, meaning that the space is not flat, is curved. It is related to the metric, but not in a simple way, right? So if you're changing the metric, you're changing the curvature tensor. If you're saying, okay, so index number I is, or mu is non-zero, so it's not index number here, right? Because the Riemann tensor has a total of 256 components, right? In 4 dimensions. Out of them, 20 are independent. So is there a simple way of saying, okay, if I know that this component or components of the Riemann are non-zero, can that immediately tell me what is happening with the space? I don't know of any simple way of doing that. Maybe it is. I have to be careful because normally what you deal with, definitely in this course, and in most problems of interest, are relatively simple spaces, right? I mean, you can say that the mathematical imagination can give you to very complicated spaces, but the ones that we know exist in nature are reasonably simple. And as we say, we're really, in some sense, interested in maximally symmetric spaces or maximally symmetric subspaces, which is pretty much what the name implies. There is some exact mathematical definition to what it is. But, a sphere, of course, is a maximally symmetric. Minkowski is a maximally symmetric. So normally we're really interested in that, thinking of a space that is curved in the sense of an ellipse, for example. You can think of that. You know what? It's a bit, the place that I think that it could be relevant, for example, is when you have gravitational waves. It's not so much for the gravitational waves because gravitational waves are really a weak field limit. So you're taking a flat space and you're making a perturbation. And it's more, if you're looking at the final stages of mergers of two black holes, then towards the end, and then maybe the metric close enough could be described by some sort of a rotating ellipse of some sort. I cannot comment much more than that on that because I didn't really do it myself. So I would imagine it's there, but it's definitely not something which is kind of a standard.
Okay, thanks.
So it's more on the mathematical side than on the side that is, well, I have to be careful. I mean, it could be that there are some people that are interested in these kind of things. I'm not one of them really. So I'm doing the simple things. These things. Okay. So, any more questions? No? None? Okay. If not, I promised you that there was one thing which we didn't have time to finish last on Sunday, so we'll do it now. It's called the geodesic deviation. So remember, the motivation is that we have a gravitational field which is it acts to curve space-time essentially. Okay, maybe I should start from a different point. Right, I motivated the whole discussion about the curvature by the need to understand Einstein's equation, namely to understand how the existence of matter acts to curve space-time. Now, it turns out that it's useful not only for that, obviously, but it's useful for many other things. And one of them is to understand the effect of gravity on physical objects. So the classical example that I discussed was, okay, we have this elevator experiment. So we have two scientists, right? They're in an elevator. And the elevator are freely falling right now, and the elevator is meaning that they cannot look to the outside, right? So can they measure gravity? And I said that at first order approximation, they cannot, because every experiment that they will do, the effect of gravity will cancel. But then I said that in fact, they do have a way of measuring it, or at least of knowing that they are freely falling in the presence of a gravitational field, or should be more precise, a non-uniform gravitational field, by the fact that they are both attracted to the center of Earth. So, if I look at the trajectories, they're both going towards the center of Earth. So that means that in their frame, most of their motion is parallel to each other, but they do have a very small perpendicular component. So if they wait long enough, on their journey to the center of Earth, they will see, or they will measure that they are slowly getting closer to each other. And this should be enough for them, assuming they're clever enough, it should be enough for them to tell that they're actually not floating in space, but rather subject to the gravitational field. In other words, so the technical term for that is a geodesic deviation. So what I do, really, I'm considering a freely falling particle, right? And the freely falling particle have an x mu of tau, right? That's a freely falling particle. And that particle, of course, follows a geodesic, as we know. And then let's consider a second freely falling particle, which its coordinates are close to the first one, right? It will be x mu of tau plus delta x mu. Right, since we particle number 2, and this is particle number 1. Of course, particle number 1 and particle number 2 both follow geodesics, and those geodesics are nearby, right? They're only changed by a small amount between each other. But that is, as we're going to see, the difference is going to be associated with the curvature of space-time. So the derivation is not very difficult because, again, it's mainly algebra that we have, right? So if you write down the equation of motion of the two test particles, So for the first one, it's of course the geodesic equation, right? D squared x mu over d tau squared plus gamma mu rho sigma, of course, a function of the position of x, right? Dx rho over d tau, dx sigma over d tau is equal to 0. And for the second one, of course, it's going to be the same, but the second is located at x mu plus delta x mu. So it will be d squared of x mu plus delta x mu over d tau squared plus gamma mu rho sigma at position x plus delta x, right, times d x rho plus delta x rho over d tau times d x sigma plus delta x sigma over d tau are equal to 0. Right? So these are the two equations that the particle trajectories follow. Now, of course, what we do in this case, we take the difference. So subtract equation 1, so equation 2, so we have 2 minus 1. And of course, take the only to the first order in the small term. First order in delta x, and delta x mu. Right, so here we have d squared delta x mu over d tau squared. And here we have several terms, so we need to simply take all of them. So d gamma mu rho sigma over dx alpha delta x alpha, right? Dx rho over d tau, dx sigma over d tau, right? I'm taking the difference between these two. Plus, because of the symmetry, I have twice gamma mu rho sigma and dx rho over d tau and the delta x sigma over d tau is equal to 0. And the 2 here is because of the symmetry, of course. Right, and I neglected terms, the derivative which will involve twice delta x. All right. Yeah. So now we can look at the relative acceleration. So the relative acceleration right, between the two nearby geodesics. A mu is d squared delta x mu over d tau squared. So d over d tau of, now we take the first derivative. Of course, it's a covariant derivative, so it's the regular derivative, d delta x mu over d tau plus gamma mu rho sigma dx rho over d tau times delta x sigma. And now we need to take the second covariant derivative. So it's the regular derivative, right? So we have d squared delta x mu over d tau squared plus d over d tau of everything that is here. Gamma mu rho sigma dx rho over d tau delta x sigma. Plus we have this extra gamma term, right? So gamma mu, let's call it alpha beta, right? Dx beta over d tau, and then everything that is in here, right? Is d delta x alpha over d tau plus gamma alpha rho sigma dx rho over d tau delta x sigma. Okay, you see where each term here is coming. I'm taking a covariant derivative, so each covariant derivative is a regular derivative plus this extra gamma term. So now it's just left to open it up. And just a d squared delta x mu over d tau squared plus, okay, now it's a bit annoying. So I take the derivative of this one and then I can simply merge it with this. So I get up with a 2 gamma mu rho sigma dx rho over d tau d delta x sigma over d tau plus, now I need to take the derivative of the second term, so dx rho over d tau. Let's see, let's hope I'm not getting myself too much confused. Plus, oh sorry, now I'm taking the derivative of gamma. So the derivative of gamma would be d gamma mu rho sigma over dx delta, then d delta tau. That's the derivative of guy. Times d x rho over d tau delta x sigma. And then I still have to take the derivative of this guy with respect to tau, so that will give me plus gamma mu rho sigma d squared x rho over d tau squared times delta x sigma. And then I'm just left with the last term. So this is this one. And then the last term that is still left is the first one. This guy I already used. And just left with the last one. So the last one would be plus gamma mu alpha beta gamma alpha rho sigma dx beta over d tau dx rho over d tau times delta x sigma. Okay, hopefully I didn't get too many typos around. It's quite annoying, but it's algebraically annoying. Just have to follow the logic here. So now I can use this equation which we derived to write down d squared delta x mu as so I have really, okay, this first term here and here is just equal these two. So I can replace them with some minus of the third term. So I ended up writing that a mu is just, let's start with this term. So this term here is just d gamma mu rho sigma over dx delta, and then dx delta over the tau times dx rho over the tau times delta x sigma. Then we have this minus term from the equation above. So minus d gamma mu rho sigma over dx alpha delta x alpha times dx rho over the tau dx sigma over the tau. And then the other terms that are left should be these last two terms. So plus gamma mu rho sigma d squared x rho over d tau squared delta x sigma plus gamma mu alpha beta gamma alpha rho sigma dx beta over the tau dx rho over the tau delta x delta x sigma. Not entirely nice, I have to say, but very much straightforward. We just again, you just follow the algebra and hope you did not miss any terms on the way. Right? So when we do that, then now we must use the Geodesic equation. Right, in the form of d squared x rho over d tau squared is just minus gamma rho and sigma mu dx sigma over the tau dx nu over the tau. Okay, now I have to make a lot of and this is one I'm going to be using here instead of that. And then I have these four terms which I'm going to write using a lot of changing of indices. So just to get the feeling, so in the first term I'm going to change sigma into an alpha and delta into sigma. And in the third term, I'm going to change rho into a lambda, sigma into an alpha, mu into a rho. And again, when I say change, of course, that is that I can always do that because these indices are dummy. Right? I have sigma both as an upper and as a lower, so I can call it whatever name I want because I'm anyway summing over it. Right? So overall, when I do this, I ended up with a mu. Remember, this is the acceleration in the u direction. It's just d gamma mu rho alpha over d sigma minus d gamma mu rho sigma over d x alpha plus I have here the two gammas, right, from the fourth term, so the gamma mu sigma lambda gamma lambda rho alpha minus gamma mu alpha lambda gamma lambda rho sigma, all that times dx sigma over the tau dx rho over the tau times delta x alpha. Now, I did not go very carefully about all the indices here because it just takes some time. It's easy for me to say, you know, I spent like 2 hours doing it properly at home, making sure I didn't get any mistake here. But, you know, so you should spend the same time and you see that it's okay. And of course, what you identify as the term inside the parentheses is nothing but the Riemann tensor. So the final outcome that we get is that a mu, the relative acceleration, right, is just d squared delta x mu over d tau squared is just the Riemann mu rho sigma alpha dx rho over d tau dx sigma over d tau times delta x alpha. Right. Now this equation is called the geodesic deviation equation. So essentially, you know, the physical meaning is quite straightforward, and I explained it to you previously. What it really means is that you know, the relative acceleration between two neighboring geodesics that goes from point to the two different trajectories that they follow, right? So when you have two, you know, freely falling particles which are nearby, there will be some relative motion, which ended up with some acceleration. And that relative motion, right, depends on the difference between them, right, the delta x, but also on the curvature tensor. The interpretation would be, of course, that this would be, you know, difference between acceleration and nearby points is really what we call tidal. It's be a tidal gravitation. Oh, sorry, tidal force, gravitational tidal force. All right. So physically, this is the gravitational or tidal forces due to gravitation. Questions? Any questions? I mean, I agree. It's just some algebra which can be quite confusing. But again, I think you got the idea by now that you know, this course requires you to do a lot of homework and a lot of not just the homework that I give you. Between you will get a new problem set today, just to keep you busy over the whole year. This course requires not just doing the homework, but going very carefully over all these things and making sure that you understand each of the steps that I made and say that I did not cheat you. Everything I did is fully legal. Yes.
You mentioned the homework. Just wanted to ask until when is the extension on the last homework?
Look, I don't know. To be fully honest, you know, I want to be the idea. My general approach, you know, I'm flexible as long as you're not trying to misuse it. See what I mean? If you're really working on it and you really have a problem, and obviously the last few days have not been standard days, I'm not going to be, you know, asshole that will tell no, you cannot do it. But if you start to misusing it, namely you're not asking on time, you say, oh, no problem, you're always allowing me, then no, I'm not always allowing you. It should be clear that I am I'm flexible with you as long as you're doing what you should be doing. Okay, so if you know now, besides, you're going to get a new problem set today. So you don't really have an interest of delaying because then you run into trouble with the current problem set. We don't want to get into that. Right? So, you know, if you need another day, another 2 days, take them. Okay, especially if you ask me in advance. But, you know, if you submit them at the end of the semester, I will not accept it by then. Okay, so try to get it in the coming days because anyway, you're going to get a new problem set.
Okay, thank you.
All right. The policy has not changed. I mean, you're supposed to hang them by, you know, after a week. If you need help, you ask for help. If you need an extension because something happened, whether it's a personal thing, you have some local peak in your other stuff you need to do, you have something personally happen to you, or, you know, there is some unforeseen events like we've had in the last 2 days, then it's fine. Provided you ask me in advance. Don't tell me, oh, I forgot to tell you what actually. All right. I'm not playing now. If you're here in this course, you're adults, right? This is not a course for kids, and you're saying that by now. So, you know, I just expect you to act like adults and not like kids. Kindergarten time, you know, is not here. All right. Okay. Any more questions? More questions? No. Again, those of you who can open your not some of you, most of you are actually opening your cameras, but some are not. If you can, please do so. It's helping me. I prefer to look at faces rather than looking at the blank black squares. All right. So, under the very reasonable assumption that everything is now clear in your head, well, finally, we gain everything we need to derive Einstein's third equation. Which is the next subject. So, as I said, this is the heart of this course, which we dig our way through a lot of math, introduced a lot of concepts, and now we're finally getting to it. And as I said, what Einstein's field equation really tells us is how the existence of matter or energy in the universe, or at a certain location in the universe, acts to curve the space-time, right? Such as we say that the space-time is curved. Now there are several ways of deriving these equations, and you can find several ways in different textbooks. I'm using one which is actually to the best way we know, and there is, you can imagine there are plenty of historians, people who are interested in the history of physics that traced each and every paper that every draft paper that Einstein ever wrote in his life, trying to figure out how the hell he managed to get there. So we're going to follow a path which is quite close to what Einstein himself did. It's my view is the most straightforward and physically motivated way. So most likely that's the way Einstein took. But I see that I also put it in my lecture notes that if you want, depending on what courses you take, some courses will derive it in a different way. you know, you can use gravity using action, using path integrals, using many things you can do. And you end up with the same equation. So I'm going to take the simplest way. And the simplest way is, you know, we start with the Newtonian, right? What is the, how do we describe physics, gravity, sorry, in Newtonian mechanics?
The force between two objects.
Yeah, that would be the 17th century. Now let's progress to the 19th century.
The field.
Yeah, it's a potential, right? So the Newtonian way, that's actually quite good. Newtonian way, right, will be the Poissonian equation. Poisson equations. Square phi is 4 pi g rho. Right? Rho, this is the mass density. Right? Now plus phi, right? Is the potential. Potential. Right. For a point-like distribution, then you know the solution. For point-like distribution, for point-like source. Really, it's a distribution. Then phi minus gm overall. Right? But again, this is for a point like. We're not limiting ourselves to any point like. It can be any configuration of masses and densities. And the nabla squared, well, it's just delta ij pi ej. This is the equation of gravity. Now the logic goes as follows. Right? If we look at the left-hand side, right, what do we see? We see a second-order differential operator. So the logic. On left-hand side, right, we have a second-order differential operator. That acts on the potential. And on the right-hand side, right, we have a measure of the mass distribution. So that is the one thing we know when looking at this equation. And the form of equation that we want, what type of equation it's going to have, it's going to look like. We want to have a relativistic generalization. So what type of equation is it going to be?
Tensor equation.
Tensorial equation. Very good, right? So relativistic generalization have to have some form of an equation between tensors. Okay. Now, once you realize these two things, you can start playing. So the right-hand side is actually quite, it's a simpler side. What would be the relativistic generalization of the mass density?
Energy stress tensor.
Plus energy tensor, right? So on the right-hand side, rho, we would want to replace with some sort of a T mu nu. Right? What about the gravitational potential? What will replace it?
Christoffel symbols?
No.
Diametric?
Yes. Yes. Right. It will be the metric tensor. So phi could be replaced by G mu nu somehow. Right? It's not exactly. So we can guess. So yes. That we have an equation that will have T mu nu on one side, which will be proportional with some constant to the second order derivative of the metric, right? Because we have here a second order derivative of the potential, right? Good. So we actually show that in class, a few classes ago, if you remember. T mu nu should be somehow proportional to the derivative of the metric. Square G mu nu. Now we showed in the Newtonian limit we showed right that if you write down G00 is minus 1 plus 2 phi, right, and T00 is equal to rho. Then the equation that we'll be looking for, remember that? We derived that? We did that. We showed you that what we call the weak field approximation, right? So we end up with an equation. So we look for an equation that predicts something like number squared H00 is minus 8 pi G200, where H00 is just 2 phi. Right? This is still the Newtonian limit, right? But generalized to a tensorial equation. That's still not the full equation, because that just tells us what should be the 0, 0 term of these tensors in the weak field approximation. Right? But it gives us a hint. So we look for an equation. All right, you following the logic so far? Yeah? No, maybe? Sort of.
Yes.
Okay. Now again, this is not yet the equation that we want, because H, you know, what we get when we have a small perturbation of the metric. We want something which is more general. Now we cannot in fact generalize that to a tensor right away. If we try to do that, and you know, first we need to change the nabla squared into a 4-dimensional operator. So what would that be?
By the second order covariant derivative?
Yeah, but you have a covariant derivative of nabla mu. So how do we call that? Put it in your homework. Right? Split it D'Alembertian. Right? All right, I posted that in your homework. Yeah? You remember?
Yes.
Yes, I just did not remember the name.
Sorry, what did you say?
We did it in the homework.
Yeah, I know you did in your homework. Okay, so we're actually going to use that. That's not going to work. Why is that not going to work? If I try to put it on a G sigma, what am I going to get?
0.
Exactly. Right? Because G mu lambda is over here. So I cannot simply put the metric on the left-hand side. First attempt, with the metric. Doesn't work. We have to be slightly more sophisticated than that. What would be the next most logical step to do? So if I cannot put, okay, I'm not sure that you're with me, right? I'm trying to take this equation, Poisson's equation, generalize it to a tensorial equation between tensors. Right now I'm seeing that in the right-hand side, I have rho, the mass density. And I know that the mass density is the 0, 0 component of the stress energy tensor. So the most logical thing for me to do is to say, okay, if I want a tensorial equation, then on the right-hand side, it should be the stress energy tensor. So now the question is, what am I going to put on the left-hand side?
Maybe Ricci?
Okay, you're quite good. You're quite good.
Because it's like Riemann, you need only two, you can only use 2 indices.
Very good, very good. So I cannot use G. The next logical step would be to put the Riemann, but the Riemann automatically, you see that it doesn't have the right number of indices. So we try to put on the right-hand side, on the left-hand side, sorry. So the second attempt, would be to put the Riemann. So put on the right-hand side, oh, that's it, it's the left-hand side. So on the left-hand side, try to put the Riemann. That's not going to work because the number of indices is wrong. So, but as you said, right? So, but rather we can use the Ricci, R mu nu. R mu nu look quite good for various reasons. For example, it is symmetric, and we know that the stress energy tensor is also symmetric, so we're quite good. So we can guess that the gravitational field equation might be something of the form R mu nu is some constant times T mu nu. What we need to do is to show that this retrieves back in the weak field limit this equation. Put it in a question mark. And then I need to find out what is kappa. Now, historically, Einstein actually did think of that possibility. It's an equation. It does not work. Why doesn't it work? Because, okay, but let me write down. It doesn't work. Why? Because when we're using the principle of equivalence, right, then the statement of energy momentum conservation how do we write an energy momentum conservation?
Partial derivative according to one of the indices.
Right, covariant derivative. So nabla mu, T mu nu is equal to 0. Right? In curved space. But if this equation were correct, that means that nabla mu or mu nu equal to 0. But the problem is that this is not true in any arbitrary geometry, right? Because when we did Bianchi identity, but from Bianchi identity, we derived nabla mu or mu nu is 1/2 nabla mu r.
So you can put it, and this is identical to 0.
Exactly. Now the problem would be that if I use that, exactly, the problem would be that if I use that in the equation back here, right, that really means that R, but R is kappa G mu nu T mu nu, which we call kappa T, right, the contraction of T mu nu. So we end up that nabla mu of T is equal to 0. Which means that T is constant. Right, because it's a scalar. So the covariant derivative of a scalar is just a regular derivative, which means that T is constant. But that doesn't make sense because T is 0 in vacuum, but T is non-zero in matter.
Maybe instead of the Ricci tensor, you can take the Einstein tensor. It might solve the
Very
problem.
good, very good, very good. I see that you're following. Who said that?
Italy. Right.
You're following. Very good. You got the idea. But T is equal to 0 in vacuum, which means that, and let me finish that, and T is not 0 in matter, like inside a star or something. Because there is some density there. Okay. So this doesn't work. So T cannot be constant. So the third attempt, as was rightfully said, is to take the Einstein tensor, right? G mu nu, remember it's R mu nu minus 1/2 R G mu nu. Now, the Bianchi identity tells us that this is always conserved, right? Remember, we did this derivative on, when was that? Sunday. Write it down as nabla mu, G mu nu is equal to 0. So now we can think of an equation of the form G mu nu is equal to kappa T mu nu. So this will be our next guess. Now, this equation looks quite good. We have everything we want, essentially, right? This is a covariant, the right-hand side here, right? This is a covariant expression of the energy and momentum density, right? This is a symmetric and conserved tensor, right? This is also symmetric and conserved tensor. Which is made of the metric, right? The first and second derivative of the metric. So that looks quite good. We just need to understand, to validate that this indeed represents gravity as we see it. Right. Let's write that made of first and second derivative. The metric. Why I write diagonal. So let's see if we get the metric, the gravity as we understand it. What do I do? Let's do contraction. So check, prove. So contract. G mu nu, G mu nu. Just G mu nu times R mu nu minus 1/2 R G mu nu. This is just R minus 1/2 R G mu nu equal to kappa T. Right? We call the contraction of T mu nu and T. Now,
Is
that's my Mac wanted to join. You're all with me? What is G mu nu, G mu nu?
Trace of G.
Well, what is it? Number.
If it is invariant, it should be 2, because 1, 1, 1 and minus. I don't know, because you have -1 in T, and then in the
What is G
metric
mu
of
nu?
Minkowski.
Yes, yes, yes. What is that? G mu nu, G mu nu?
Oh, but there is minus, so it's 4. No, I forgot there's a minus. Yeah.
Thank you. Very good. You all see that? In flat metric, right? G is equal to eta, and so eta 0, 0 square plus eta 1, 1 square plus eta 2, 2 square plus eta 3, 3 square. This is 4. And this is a tensorial equation. So if it's true in one system, it's true in any system. So it's always 4. So we ended up that the equation is R is equal to minus kappa T. Yeah? I know it's damn confusing. That's exactly why you have to do it and do it and do it, and then you see that actually, oh, it's quite easy. Okay, so using that back in here, I can write it down as R mu nu is equal to kappa T mu nu minus 1/2 G mu nu T. Yeah. So this is the same equation as I wrote here, just written in a slightly different form. Okay. Now I argue that this equation predicts the Newtonian gravity, right? Again, in the correct approximation, which means that the weak field and then time independent and slowly moving particle. So in the limits, right? Weak field, and then time independent, and slowly moving particle. So in this limit, of course, we have T00 is what?
Rho.
Rho, right? That's how we started. I actually want to encourage, some people here are participating, which is great. That means that you're on that and you follow. Some people are a bit more shy or more quiet. I want to encourage everybody to participate. Okay? No need to be shy. It's not the place to be shy. So T00 is rho. And that's, of course, that's going to be much greater than all other terms. Essentially, like rest mass energy is much greater than the kinetic energy, right? And so we can only take so it's going to be the much greater than T mu for mu and then 0. So I can neglect those. So I can set only, so look only mu equals 0 terms. And now in the weak field limit, remember we discussed that we had G mu nu is eta mu nu plus H mu nu, or H in absolute magnitude is much more than unity. Right? And then again, G is an upper indices, is eta is an upper indices minus H is upper indices, which of course follows from Taylor expansion. So we have G00 is just minus 1 plus H00. G00 is a minus 1 minus H. Sorry. 00 is a lower indices. It should be the same upper indices here. It wouldn't matter. We can check it out. Okay. So the trace of the energy momentum tensor T is T00, T00. It's going to be a minus T00, first order. And I'm going to put all that in here. Then we're left with R00 is 00 is just going to be 1 minus, so I just have a 1/2 kappa T00. -1. So the -1 here, this is a -1. This will be also a minus T00. So the minus will cancel, so I have a -1/2. So T00 minus 1/2 T00, so 1/2 kappa T00. Right? Okay, so this is the question for R00, which is the derivative of the metric related to the energy density. So if we really want to get the full expression for the metric, then there is no way. We actually have to go through the full calculation. And R00 is just getting the contraction, right? It's just R lambda 0, lambda 0. Now, since R with all zeros are 0, then we only care about R00, Ri0, I0. We only care about Ri0, I0. Since R0, 0, 0 is just 0 because the metric is given flat. So Ri0, J0 is just d J gamma I 0, 0 minus d 0 gamma I J0 plus gamma I J lambda gamma lambda 0, 0 minus gamma I 0 lambda gamma lambda J0. So by definition, okay, now it's actually not too bad because let's see.
Wait, Asaf, but don't we need the same index?
Sorry? What did it say?
Don't we need like I equals J because we have a contraction lambda,
Oh, yeah,
lambda,
we will.
lambda?
Yeah, we will. But right now I'm just doing it in a more general way. You see, it doesn't matter.
Okay.
We will. Yeah, of course. Now this is a time derivative, and the time derivative is 0 before the static metric. Right? D0 is equal to 0 because the metric is static. This is the second order terms, right? But we say that there is a small perturbation, so really it's a perturbation squared. This is the second order. The perturbation. So I can remove those as well because they're too small. So the first order we have, so first order R00 is just be just R I0. It's just B I gamma I00. I write it down again. Open it up for expansion. So it's 1/2 G I lambda D0 G lambda 0 plus D0 G0 lambda minus D lambda G0. Now again, the metric is static, so these two guys cancel out because it's a static metric. So the left is minus 1/2, and then we have eta ij vi dj of h00. which is another way of simply writing minus 1/2 nabla squared 800. So in the Newtonian limit, so the conclusion of this exercise, in case for some reason you got lost, right? In the Newtonian limit, right? Again, weak field, static, right? It's here, time independent, slowly moving. In the Newtonian limit, we have that the 0, 0 component right, of the attempt that we made of G mu nu equal kappa T mu nu is nabla squared 800 is equal minus kappa T00. But when we compare that to the Poissonian equation, which we derived previously, here, I see that I got the same equation provided I put down kappa equal 8 pi g. And the equations are equal. So what we just showed is that in the Newtonian limit, if we take this equation here, and identify the constant kappa with 8 pi g, we end up back with the Poissonian equation, which is familiar from classical mechanics. But of course, this equation is much more general. It is a tensorial equation, and it is true not only in this limit, but in any limit. So having this normalization, we can finally write down the Einstein field equation G mu nu, which is R mu nu minus 1/2 of G mu nu is equal to 8 pi G T. This is Einstein's field equation. On the right-hand side is the mass term. Right? It tells us what is the distribution of energy and momentum. On the left-hand side is a geometrical term. Right? This tells us how the curvature of space-time reacts to the presence of energy and momentum or mass. Right? Okay, take a second to appreciate what we just wrote here. Also appreciate the way we went through. I've been going through this course several times. I always try to see if there is any way that I can do a shortcut to get you to this equation without going through the entire math, and I couldn't find anything. And if you go back to what we did so far, you'd see that we actually needed all the steps in order for you to fully understand what is actually written here in this equation. Right. I should express it. Einstein's field equation expresses how presence of energy, mass, source curves space-time. Essentially, we got to the focal point of this course right now. Pretty much what we're going to do from here on is to find solutions to this equation. Now, nobody knows if we find all the solutions. I'll tell it to you in a second. What we're going to do in this course, we're basically going to speak about 2, maybe 3 solutions of this equation. The 2 solutions which we'll certainly speak about is one, the vacuum. So a vacuum is T mu nu is equal to 0. In fact, you already know one solution of the vacuum, right? This is the Minkowski metric. Right? That's a trivial metric. There is another solution, which was found by Karl Schwarzschild. That's called the Schwarzschild solution, and that represents black holes, which we will discuss thoroughly. Again, when we say vacuum, I mean, sometimes it can be quite confusing. You know, vacuum means that there is nothing in the, in that space, but the space can be in the vicinity of some source of curvature. Right? Same as an astronaut is floating in space, but is affected by the gravity of Earth, which is nearby. Right. So that's called the vacuum solution, where I can put T mu nu equal to 0 on the right-hand side. The second solution that we'll discuss is a solution about the entire universe. Now, the entire universe contains matter, so we cannot say that it's empty. It's not empty. T mu nu has something, some matter context, and that is the basis of what we call modern cosmology, the Big Bang. The solution is called Friedman-Robertson-Walker, FRW method. And that is the solution that describes the expansion of the universe from the Big Bang until today. We will discuss that. If time permits, we will discuss a third solution, which is a weak field that leads us to gravitational waves. But that's, again, the reason why I'm not putting it in the first is because it's more technical than the others, and I think it contains somewhat less physical insight than the others. It's much more heavy algebra of the type you've already seen. It has some interesting consequences, of course, but it's more technical than and you get less physical insight. Now there are other solutions. I mean, solution for there are a few known solutions. There is a solution of the Kerr metric, for example, which is a generalization of the Schwarzenegger metric that describes rotating black hole. I don't think we'll have time to discuss them, though it's very fascinating. It's, Event Horizon Telescope showing the black hole that is actually deduced from what you saw that it's actually rotating. Now, how many equations do you see here, by the way? 16, right? There's really 16 equations here. Are really 16 equations. They are extremely complicated. Think of it. in order to get to these equations, right? What we need, it's a differential equation, right? When we say a solution to the equation, what do we mean? I mean that I'm giving you some distribution of mass, right? So you can, or flow of mass. So I'm giving you T mu nu, and I'm asking you find me the curvature or find me the metric that will lead up. Now on the left-hand side, right, I have the metric. I have the first and second derivative of the metric, which I need to get to the curvature tensor. Then I have a contraction of that, right? So, and this equation, this is a nonlinear process that we have here. We have all sorts of terms here, and they are not linear. Nonlinearity means that if I happen to know two solutions, a linear combination of these two solutions is not a solution. So you actually have to solve a solution by yourself, right? Now, there are people dedicating their lives trying to find solutions to these equations. By no means we can tell that we find all the solutions. We haven't. We just don't know what the solutions are. Like more than 100 years after it's first introduced, we only have a handful of solutions that we know that work. We simply don't know. Nobody knows. This equation was introduced by Einstein in 1915. This is Einstein. 1915. It's been more than 100 years. Many solutions we don't know. We know only a handful of simple solutions to this equation. Now, we said there are 16 equations. They're not all independent. The fact is that there are only, right? There are 10 independent equations. The rest you can find, you are connected by the Bianchi identity because that gives us some constraints. So really, there are a total of 10 independent equations. Namely, there are 10 unknown functions of metric components. Sorry. Sorry. Okay, my mistake. There are only 6 of them. There's only 6 independent. There is a way to get to. Sorry. Yeah. There are 10 independent equations. My mistake. 10 independent equations. That's right. But we have the Bianchi identity. Plus Bianchi identity. Bianchi identity implies that there are total only 6 unknowns. Because the rest are, you can get them by the Bianchi identity. So in reality, there are really only 6. 6 independent equations. Yeah, the 10 and not 16 is because these are symmetric. Right? R mu nu and R nu mu, since they're symmetric. Remember when we spoke about symmetric matrix, it has only n minus 1 independent, n plus 1 independent terms, because the other ones you can get to them by symmetry. Okay, we said these are extremely complicated, involve derivative and products of the Christoffels. I don't think I forgot anything. Now, of course, in order to find solutions, what we really need is to get symmetry. So one of the things we'll do, the first thing we'll do, next lecture, we'll start to discuss if we can find a simple way of seeing symmetries in this equation. But before we're going to do that, there is one last bit which is worth noting, because if you're already here. And that is the following. We look at this equation. Let's look at Einstein's equation in vacuum. Right, vacuum meaning T mu nu is equal to 0. So then Einstein's equation is R mu nu minus half R G mu nu equal to 0. Now I can add a constant here. It may be in a different color.
It's a constant on a scalar function.
So it's the same. It's constant. Right, no, it's not a function, right? It's just a constant. Lambda is constant. And the reason I can do that is because when I take the covariant derivative of the metric, it's always 0. Right? Scalar function means it's a function which changes in location. Constant means it's the same value everywhere. How do I call this term?
Cosmological constant.
Sorry?
Cosmological constant.
Very good. The cosmological constant. I can always add it to the equation. So that's the cosmological constant. Okay. Now, I don't know if you know this story, because this is one of the most interesting stories in the history of physics. Who put the cosmological constant? You know?
Wasn't Einstein?
It was Einstein. Why did he do that?
Because he believed the universe is not expanding, like it's constant.
Okay, exactly, right? So when he wrote the equation, then he started to look for solutions, and he could not find any solution which would predict the universe that is steady. Always find the solutions of the universe that is changing, expanding, or okay. And then he realized that he can add up this constant and he get the universe that is steady. And of course, the reason why he wanted to do that is because in his time, it was believed that the universe is infinite and is steady in time. It was only about 10 years later that Edwin Hubble proved that the universe is actually expanding. And legend said that Einstein, for that, called this the biggest blunder of his life, because hadn't he insisted on putting this constant just to be there, then he would have predicted that the universe is expanding 10 years before Hubble. Now, you have to be even more careful, because you can put a constant such that the universe will be steady, but then the equation is not stable. That means that if you're slightly changing the value of lambda, you have to put a very specific value of lambda to get a steady universe. Right? If you're slightly changing this value, the universe will collapse or expand wherever. It will not stay. It's an unstable solution. So that's called the Einstein's biggest blunder, right? That's how it's called in a lot of popular history, science history textbooks. Now, even more interestingly, so after Hubble discovered that, I think it was 1929, Einstein took himself and said, okay, it was really stupid, and forget it, and then it was removed. And then suddenly, 70 years later, it made a huge reappearance. Do you know when? Why? I just said when. Do you know why it made a reappearance, this cosmological constant?
Cosmic microwave background, maybe?
No. That was interestingly, again, related to Hubble. This was the most important discovery made by the Hubble Space Telescope. You know what is this discovery?
All galaxies move apart from each other?
That Hubble himself discovered. The man Hubble discovered. What did the Hubble Space Telescope discover in 1990? 1999. That was the Nobel Prize, I think, in 2013 for Adam Rees and Saul Perlmutter. The Hubble discovered that the galaxies do not only recede away from each other, but that they actually accelerate. So the universe is not only expanding, as you can imagine, it might also, it is actually accelerating away. The galaxies move away faster and faster with time. How can that be? Because all the gravity, all the forces that we have here is attractive, right? Gravity is attractive. So you can envision a situation where there was some initial energy causes expansion, but then gravity attracts, right? You have your T mu nu, which always attracts. So how do you resolve that? You take this part here and you move it to the right-hand side. Now, when you move it to the right-hand side, right, the right-hand side, right, is the physics side, right? That's where we put the matter. So if we put it to the right-hand side, we can think of it of some addition to the energy momentum tensor. So on the right-hand side, right, we have T mu nu effective is minus lambda G mu nu. So it's some sort of a minus, a negative energy momentum tensor term. Right? How do we call that same term when it's occurring on the right-hand side?
Dark matter.
No, this is dark energy. Right, and this is the dark energy. There is no matter here. And it has a negative sign. So it contributes to the vacuum. The more vacuum you have, the more energy is in there. So it's exactly the opposite of what you'd imagine that there should be, right?
Wait, but the energy tensor is come from a real matter, so the dark energy doesn't come from, you know, dark matter?
No, dark matter is something else. That's called dark energy. I will say a few words on dark matter. I won't do it today because we're already running late. No, this is called the dark energy. Now, the other way of thinking of it is like this is the energy density of the vacuum.
So it's like a quantum effect, or?
Oh, now we're getting there. Now here is the fun thing. Quantum field theory actually predicts that vacuum should have energy of itself. Why? Is because the way we understand matter today in the form of quantum field theory is like oscillations, right? You have a field, each particle, there is a field associated with it, and these fields oscillate. So it's very similar to simple harmonic oscillators that you learn in quantum mechanics, but in the form of fields, right? And an excitation of these fields causes particles. This is a quantum field theory, right? That's the way we understand now. So the ground state energy, which is the vacuum energy, right? The same way as in quantum mechanics, it's never zero, right? It's 1/2 h bar omega, right? So here too, in quantum field theory, we also have that. Now, of course, there is some, mathematics that need to do that, but essentially, when you do that, you ended up that you can calculate that the vacuum should have some sort of energy. But now comes the problem. When you are comparing the theoretical prediction, right, of the energy density of the vacuum with the theoretical, with the observational results of the cosmological constant. They don't match. The values that the theory predicts and the value that you're seeing do not match. Do you know how big is the difference? Don't have to know. Do you want to guess how big is the difference? Factor of 20%, 100%, factor of 5. Does anybody want to guess? Everyone needs to tell you the answer without even trying to guess. So the answer is 120 orders of magnitude. 10 to the power 120. That's the difference between the theoretical prediction and the observations. This is the largest difference in theoretical physics that exists today. It's the difference between theory and observations. There is something very fundamental about this whole nature of dark energy that we do not understand. We know it's there. We see it's there. It's dominated. 70% of the energy in the universe is in this form of dark energy. And we've got no clue what's going on here. Of course, the value that you put to explain observations with lambda is not the same value that Einstein originally put, but a different value, but it doesn't matter. Okay, so that was the Nobel Prize in Physics for a few years ago. And it's clear that something very, very basic is unknown. All right, guys. Cool. I told you this course is going to be cool, and it's going to get better and better. We still have to do some more math, but you'll see that things are going to get better and better from now on. Any questions?
Can you take any other field and apply the same tricks we did today and find how it curves the space-time?
Yeah, if I understand correctly, the question is can you calculate what is the effect of the different fields on the space-time, right? Is that what you asked?
Yes, exactly.
Yeah, well, you can do that. But again, we'll discuss that when we discuss cosmology. We know, what is the we can measure what is the density of particles in the nearby universe. So we can estimate. So we have these measurements from data, and then it's yeah. So we basically can do these calculations. Again, the difference is what I just said. It's, 120 orders of magnitude. You're not going to get past that. Okay.
Yes, thank you.
Okay then. Sunday there is a holiday, as you know, so we won't meet this Sunday. We'll meet again next week, next Thursday. I'll post the next problem set. I wish you all to have a quiet and a pleasant weekend in general, and hope to see you all again next week. So stay safe, stay calm, and things will pass. We'll get better. And stay, interested in this one. Pretty cool, isn't it? All right. Any further questions?
I have about the homework.
Yes, then that's you can ask me after we finish. Any more?
Bye, Sam.
Bye-bye.
Bye.
I think.